23, creating J psi in E plus E minus annihilation. J psi is a pair of particles. In this composite particle consists of a charmed quark and anti-charmed quark. In nature, there are electrons, and atom consists of electrons and nucleus. And nucleus consists of protons and neutrons. And proton consists of up quark, down quark. You know, the charge of the proton is a plus E, and actually it is plus consists of 3 quarks. Each quark has up quark has a 2/3 of electron charge, and there are 2 up quarks, and down quark. Down quark has a minus 1/3 of electric charge. So hence, if I sum them all, we have plus E for the proton. And neutron consists of UDD, and it is 2/3 plus and 1/3. So it is neutral, electrically neutral. That's the reason why it is a neutron. Neutral, neutron. And this is proton. And in nature, there are up, down, charm, strange, top, and bottom, 6 quarks. Until now, we have found these 6 quarks. There are leptons, such as electron, and leptons, electron neutrino. Electron neutrino, that is massless. Both of them a spin half particle. Electron, mu1, and tau, and corresponding neutrinos. So quark, lepton, and gauge boson. So photon is the gauge boson that mediates the force, electromagnetic force. And W plus minus and Z0, these are the mediators of the weak interaction. And there is a strong interaction that is mediated by gluons. And these strong and weak and electric, so electro-weak interaction and strong interaction governs the nature of this interaction of the quark and leptons. This is the word nature, the basic elements of nature, what we know until now. You'd like to know what's happening in case we supply energy to create a mass. This is an example. We have a collider right now, Large Hadron Collider, LHC, is running at the moment. Is a very, very high energy collider, but at low energy level. When it was discovered, when this particle was discovered, it was still the greatest energy available. So electron and its antiparticle, positron, the same mass, but its electric charge is different, opposite. They collide. Einstein's relativity states that the force momentum p mu has the 4 components: energy divided by the speed of light and momentum. And we remember momentum is a mass times velocity, and the mass is not fixed. Instead, it's a rest mass divided by this factor that is called Lorentz factor. And energy is correlated with the momentum. And remember, this is the master formula that relates to energy and momentum. And this is because the p squared, that means zeroth component squared subtracted by the spatial part, this is invariant on the Lorentz transformation. The value is m0c squared, where m0 is the rest mass, that is the mass of a particle at rest. So from in this lecture, we just remove 0. So if I write the mass, either small m or capital M, they indicate the rest mass. So rest mass of an electron is 1.5 mega electron volt per speed of light squared. You can see m0c squared. If I remove the mass after the disappearance of the mass of an electron, you will generate 10 to the 6 electron volt. In comparison with the mass of an electron, the mass of J psi is very, very heavy. What's that? Giga. 10 to the 9. The difference is 6,000. Really heavy. Okay, if I prepare a collider, electron is coming in along this direction, and positron is coming in along this direction. At the center of a momentum frame, that means they are making head-on collision with the same velocity, or either same linear momentum. So electron and positron are making a head-on collision. Therefore, because the mass of the electron and positron are all the same, if I substitute P or minus P, I have the same amount of energy. Therefore, this electron and this positron, they have equal energy and they have opposite momentum. And we would like to let them collide. And suppose that after the collision, a particle called J psi has been created. We'd like to see if it is possible. Yes, it is possible. Einstein's relativity is confirmed in the sense of energy conservation and momentum conservation. We call it energy momentum conservation, that is for momentum conservation. So if I let these two particles collide, the sum of these two four momenta becomes a single momenta, four momenta of a J psi that is produced. And because this sum, P1 plus P2, is 2E over C and 0, that must be the same as the four momentum of J psi. That is at rest. It is not moving. So let me call it capital M C squared divided by C, so MC comma 0 is the four momentum of J psi. And this is a sum of electron and positron. So Einstein's four momentum conservation states that they are equal. and 0 equals 0. That's fine. So mc should be the same as 2e over c. Multiply, divide energy of an electron is 1/2 mc squared. That is the energy of positron. So I add this 1/2 mc squared, 1/2 mc squared, the sum is mc squared. I have created a particle of mass j psi. So the sum of the four momentum is like that. Square of this is mc squared. As a result, I have obtained this constraint, as I already explained on the previous page. What is the magnitude of the free momentum of the electron? Let's see. I know the energy of the electron and positron. Both of them are expressed as the square root of mc squared plus p squared because both of them has the same magnitude of momentum, and both of them has the same mass. That's why. So substitute this expression in the previous constraint. What I get is this. So why don't we square this to find that is of m squared c squared over 4 and mc squared plus p squared. Move this guy to the left hand side. So the answer is this. So squared, p squared has the value, and the absolute value is just the square root of this, and that's fine. Find the value of p, absolute value of the free momentum, if two particles of mass m1 and m2 annihilate to create a heavier particle. Okay, this is a little bit different story. So asymmetric collision due to mass, two different masses. This particle has m1 and this particle has m2. Still, it's better to consider center of momentum frame. In Newtonian mechanics, we always studied the center of mass frame, and at the center of mass frame, the total linear momentum vanishes. Unfortunately, that is not true for relativity, and more fundamental frame of reference is not the center of mass frame, but the center of momentum frame. Anyway, I choose a frame in which the two colliding particles has the same magnitude of momentum, but sign is opposite to make the sum has a vanishing free moment. Unfortunately, even though the two momentum has the same magnitude, energy should be different because they have different masses. As a result, if I substitute this one to the energy conservation formula, we have mc, comma 0, that is the resultant for momentum of the final state particle, and this is equals E1 plus E2 over C, and sum of these is a 0. So I need to solve this equation. This equation, you are familiar with this kind of style. Okay, I missed to put p squared. When you want to solve the trajectory of an ellipse, the sum of distance from to foresee. There is a focus, another focus, distance, D1 and D2, and we would like to find the track in which the sum of these distances become constant. And the solution is ellipse. And to solve this problem, you have a similar structure. So remember how to solve this. First of all, you have to remove one square root. So it's better to simplify the expressions. Let me write this one to be Z, and M1C here as X, M2C here, and Y. Then the expression becomes, because Z equals the square root X squared P squared plus Y squared plus P squared, I subtract this. So Z minus the square root X squared plus P squared equals square root Y squared P squared. And then we take the square. And this square root disappears in here, but in here we have square and disappeared square root. However, still we have the 2 times crossing term, 2 times Z square root. I need to move this guy to the right hand side and square again. Before that, I find this P squared cancels. And then if I move this one to the left, Z x y square plus minus. And this guy has been moved to the right hand side, and this minus negative sign becomes positive. Let us square both the sides. Then 2z becomes 4z squared, and this x squared p squared. And this one is square. Okay. A little bit busy. However, we can do the job. We have this one 4z squared x squared plus 4z squared p squared. I'm interested in solving this p squared. So 4z squared p squared equals square, subtracted 4z squared x squared. You find plus and minus z x y. You know, this is what? Something squared minus something squared. So that is always factorized into 2 pieces. Okay? So what is something? Z squared, x squared minus y squared. What's that? This is a 2zx squared plus 2gx and minus 2zx. Okay? And then we have zx here. Oh, it's just z plus x squared subtracted y squared. This is z minus x squared minus y squared. Again, I make use of this factorization formula to find that it is completely factorized as a 4 factors of four linear factors. And I have divided the equation by 4z squared to arrive at this point. You remember, this is compactly expressed in if I introduce a function, very symmetric function, it is called the Kellen function, the particle physicist. And finally, this factorized form is completely expressed in terms of this Kellen function and the magnitude of a free momentum. What is the free momentum? Okay, to create a particle of capital M with a collision of 2 particles of different masses with momentum p and momentum minus p, then you can create a particle of mass m that is greater than the sum of these two masses. And actually, this this kind of form appears in the Heron's formula, but the sign is opposite. Sign is opposite. All right.